thank you very much for the invitation. And I'm really excited now to be part of the bp-ICAM program and vision. I also to say that, as George just said, I'm going to be talking quite a lot about electrocatalytic processes, but I'm not an electrochemist, I'm a photochemist. And this work, particularly on the side of electrolyzers, is very much a collaboration between me and my own group and Ivan Stevens, and particularly our link person, Reshma Rao. And much of the electrocatalysis work you'll be hearing about later is certainly jointly with Ivan and Reshma, and indeed often guided by them. What I thought I'd do today is talk, in essence, what I'm going to be doing today is talk about the idea that when you try and analyze the performance of a catalyst, then of course the classic way to analyze performance is a current voltage curve. And that current voltage curve gives some indication of overpotential required to drive a certain current density of, ideally in this case, water oxidation. But what I want to talk about is the insights which I think that the approaches which we develop in my group based upon optical spectroscopy can give to that. And the essential idea there is that very often we're dealing with transition metal oxides. And transition metal, they're one of the most widely studied classes of materials for electrocatalysis. And transition metal oxides have the property, and indeed in general transition metals have the property, that their redox states are colored. And we can monitor the presence of different redox states simply by measuring the optical absorbance of the electrocatalyst, either in transmission or in deflection. And this is essentially the concept here, that if we simply take our electrocatalyst or indeed our photocatalyst film, when we apply a potential to it or we shine light on it, then we can measure performance not just by the current as a function of voltage or light intensity, but by the change in optical density of the film. And that ability to measure optical density, which gives us a direct handle on population, and maybe more interestingly, enables us to discriminate between different redox states, so different populations, gives us an additional handle on trying to understand how these wonderful materials work, or mysterious materials work. I'll start off by giving a few brief thoughts on the motivation, which I know is already something which bp-ICAM is thinking a lot about, sustainable fuels and chemicals. I'll touch on the distinction of the opportunity and the challenges of electrocatalytic and photocatalytic pathways. I'll introduce the concept of using operando spectroelectrochemistry. Then I'll talk a bit about what we've been doing on photoelectrodes, which actually we started with this work in the area of photoelectrodes before electrocatalysis. And then I'll go on to focus on the work which we're doing, particularly with the bp-ICAM program, on electrocatalysis, and focus particularly on Iridium Oxide, with the current state-of-the-art electrocatalyst for PEM electrolyzers for water oxidation. So the motivation for sustainable fuels and chemicals, I think, is becoming increasingly understood. It's the challenge that we're moving rather well towards at least starting to decarbonize our electrical power generation. Okay. But if we really want to decarbonize our global energy system, we have to go well beyond decarbonizing power or defossil fueling power, and think about how we can synthesize fuels and chemicals at scale using sustainable energy. We also have a challenge of storing energy, and hydrogen and storing energy in chemical bonds is probably the most scalable way to store energy. It also offers the potential of how we can move sustainable energy around the planet if we can synthesize, for example, either hydrogen or maybe more likely ammonia or hydrocarbons using sunlight or wind and carbon dioxide. And that gives us the potential, at least, to start to think about a global sustainable energy system, not just for making electrical power, but for making sustainable fuels and chemicals. But of course, achieving that's non-trivial. We have to do it at a massive scale, and we have to do it at a low cost. A rather simpler picture is the idea we want to make green hydrogen or maybe green ammonia, or to make sustainable hydrocarbons. This is quite a nice concept, the idea that we can turn sunshine into a liquid fuel we can then transport around the world. My own particular interest is in solar processes. Of course, there are multiple sources of renewable power, of which in the UK wind is particularly important, but I have a particular bias towards solar. And in some ways, what we're talking about here is akin to artificial photosynthesis. It's the idea that plants already have an understanding of how they can harness sunlight to make biomass by reducing carbon dioxide to hydrocarbon or based fuels. And we want to try and achieve that using chemical processes. But the motivation, of course, is that whilst biology is already can provide a fantastic inspiration, already there's challenges between biofuel synthesis and food production. And equally, plants did not evolve to have particularly high rates of overall conversion of sunlight to useful energy. And we would like to develop systems which are able to convert sunlight into storing that energy into chemical bonds, and particularly do that in ways which don't involve competition with food production. And there are now many initiatives around the world trying to achieve this. You can see just some examples of those in this region here. It's also an area of mission innovation. And indeed, it's already possible. It's possible to take solar cells to make electrons, to use electrons to electrolyze water, to make hydrogen and oxygen, and then use hydrogen to reduce CO2 to carbon-based fuels. The challenge, of course, is that currently that's too expensive. And we have to think about how to develop approaches which can lower that cost and start to make it cost competitive with fossil fuels. I'm going to focus particularly on this middle challenge here of trying to split water into hydrogen and oxygen, either directly using electrons or by the sunlight to drive the photolysis. Another way of viewing that in terms of how we could configure systems is that, of course, we can take a solar cell and couple it to an electrolyzer to split water into hydrogen and oxygen. And already that starts to become of interest. But currently, in most contexts, the hydrogen synthesized by that route is more expensive than the hydrogen synthesized from methane. Of course, the hydrogen from methane results in CO2 emission unless you store that CO2. And so that's currently, which is of course the major concern. But we need to find ways to be able to bring down the costs. And one way to bring down the cost is make cheaper solar cells. The solar cells are already now becoming quite cheap. Clearly, we want to find ways to bring down the cost of the electrolyzers and also think about the integration. But you can think also about integrating these processes of light absorption and electron and hole generation and the catalysis in more integrated devices. And these can either be as photoelectrodes or indeed as particle suspensions, where light shines on a semiconductor, generates electrons and holes, and with appropriate catalysts, those electrons and holes can drive directly the reduction of hydrogen and oxygen. Currently, the only examples demonstrated at scale are the PV plus electrolysis. Cost analyses suggest that if we could achieve efficient performance with particle suspensions, these could have significantly lower costs than bringing than the PV plus electrolysis. Whether that's going to be achievable is not clear. There does start to be demonstrations. So this is a demonstration from some groups I work with in Japan, where they're demonstrating photocatalyst sheets to split water into hydrogen and oxygen at the 100-meter square scale. And that system has already been working for several months. And it's based upon a photocatalyst of Strontium Titanate, which actually, when you can achieve quantum efficiencies, so the efficiency of turning, in this case, UV photons into hydrogen and oxygen is almost 100%. But of course, the problem here is that that only works in the UV. This photocatalyst doesn't work in the visible. And in order to get something useful in terms of, we're going to need to develop catalysts which work under visible light. What all of these approaches have in common is that they need to take electrons from something in order to reduce protons to hydrogen. And by far the most scalable substrate for taking electrons is water. And the challenge is that the oxidation of water to release molecular oxygen, which you can see here, is kinetically and thermodynamically difficult. And that is the fundamental bottleneck which limits all of these approaches. So if we look, for example, at a PEM electrolyzer for splitting water into hydrogen and oxygen, and look at what limits of what limits the efficiency of this device. And so what you've got a plot here of applied cell potential versus the current density being delivered by that electrolyzer. At the equilibrium potential at the operating temperature is 1.17 volts. So in principle, you could oxidize, you could split water into hydrogen and oxygen with a voltage of 1.7 volts. In practice, in order to achieve any sort of reasonable current density, you need to apply a potential which is 300 or 400 millivolts higher than that. And when you analyze why you have to apply a larger voltage, nearly all of the overpotential comes from the overpotential required to drive the water oxidation, which for a PEM electrolyzer would be iridium oxide. And essentially the reason there is that water oxidation catalysis is slow. And that if you want to accelerate that catalysis to a current density which is useful for a commercial device, you have to apply a large overpotential. We see the same thing in plants. So plants oxidize water. They don't use an iridium catalyst. They use a manganese oxide cluster inside a photosystem. But if you look at the performance of these proteins, these photosystems, which oxidize water and take the electrons ultimately to reduce CO2, then they have a kinetic challenge. The lifetime of the chloride excited states is nanoseconds, but the catalysis of water oxidation is again slow, milliseconds to seconds. And plants use around half of all the energy from the sun which they absorb to gain the lifetime of the charges to drive the catalysis. So this idea that catalysis is slow cuts the efficiency of plant photosynthesis by about 50%. We've seen the same thing in artificial systems. And so this is an example of data for metal oxide, where the fundamental excitations in metal oxides typically live for picoseconds or nanoseconds. The water oxidation catalysis is again slow. And so these systems lose energy to gain the lifetime required to drive the catalysis. We've done analyses of this, in this case, comparing photovoltaic and photosynthetic systems and looking at how much lifetime gain is required to drive function versus the energy loss associated with that function. And indeed, we always find that if you're going to try and split water, then the energy penalty is bad. And that's all around the idea that catalysis is slow. So when we want to think more about water oxidation and why it's slow and what determines the kinetics, then there are many models of function. And here are just two examples. Many people consider, for example, on simple metal electrocatalysts, that you can imagine single site mechanisms associated with the binding of oxygen, the forming of an OO bond, and the release of oxygen from that metal substrate. You can also imagine multi-site mechanisms. So this manganese cluster in plants the function of this system is associated with the accumulation of essentially 4 oxidizing species, which then come together to oxidize 2 molecules of water to 1 molecule of oxygen. One of the key challenges here, of course, is the idea that this is multi-redox catalysis. So in order to get 1 molecule of oxygen, you've got to extract 4 holes from 2 molecules of water. And that's complicated because you've got to have 4 holes coming out of the same site. And then you have to try to understand whether the catalysis is going to be limited by the electrochemistry, by our ability to generate oxidizing species, or by the chemistry, for example, of OO bond formation. There's many ways to analyze this sort of behavior. One way to analyze this, which I'll come back to a bit later, are theoretical plots like this. We'll look at overpotential required to achieve a certain current density versus the energetics of oxygen and OH binding to the metal on the surface. Another way to think about what determines the catalysis is to think about activation energies. And so the idea that as you apply a higher potential or you have a higher coverage of oxidizing species, then the activation energy comes down in some way. And we'll talk about that a bit more later on. Another viewpoint is simply the idea that if you got to do 4 oxidations, then having a lot of oxidizing species around to come together to drive a catalysis is going to accelerate things. And so the idea of that when you apply a potential, the main thing you are doing is simply generating more oxidizing species. And when 4 oxidizing species come together, they can oxidize 2 molecules of water to 1 molecule of oxygen. These are all different models. What we've been trying to do is to think about how we can use our optical spectroscopy to interrogate those models, and particularly then to think about how that can give us insight into why one material might work better than another. And so, or how changing material structure can enhance performance. We'll see an example of that later when we talk about iridium oxide and thinking about how we can reduce the iridium content in an electrolyzer. And so the idea here is that we're going to take our electrocatalysts, and these are typically going to be films. So we're not actually studying complete electrolyzers. We're typically studying the electrocatalyst deposited on a substrate. We apply a potential. We start to see a current, which is the water oxidation current. And very often we start to see bubbles. And then at the same time, we measure the optical absorbance of that electrocatalyst or that photocatalyst, most simply in a UV-vis spectrometer. We actually don't use a UV-vis spectrometer. Fortunately, one of my group, Ben Moss, has been very skilled at building detectors to measure the optical signals at high sensitivity. Actually, one of the problems we have is, of course, that if you get a lot of bubbles, that makes it much harder to measure the kinetics. And so we have to try to measure the optical absorbance change before the bubbles start to form by using pulse sequences of the voltage or light. I'll start off just talking a little bit about what we did with hematite, which is not the most exciting material in the world. Essentially, it's rust. We look at nanostructured rust because it's got a high surface area. It comes from Michael Gratzel at EPFL. But it's a visible light absorbing material. It's an oxide which is able to drive water oxidation, and it's remarkably stable. Everyone is probably aware that as anything metal degrades, it tends to end up as rust. Anything iron degrades, it ends up as rust because rust is stable. And so we've been looking a lot at the kinetics of water oxidation on hematite. And what we were interested in trying to measure is we shine light on this electrode under some potential. We drive holes to the surface, and we want to try to measure how quickly these holes react with water to make molecular oxygen. And so the way we do that is we apply a positive potential to make sure we can drive holes to the surface, and then we shine some light. And we measure, typically we shine light for 5 seconds as a pulse, and we measure the appearance of a current, which is the water oxidation current, which is on when the light's on and goes off when the light goes off. But in parallel with measuring that current, we measure an optical signal. And that optical signal, we measure a particular wavelength, 550, which we've been able to show corresponds to a formation of iron 4 oxo species on the surface, which we believe are the states which are driving the water oxidation in this system. We're able to measure the population of those states accumulating on the surface by their optical absorbance. And then we can change the light intensity, and we measure how the current density changes, and we measure how the density of holes at the surface changes. And when we do that, we can then plot the current versus the number of holes at the surface. And we get, in this case, a rather striking and simple behavior that at low is first order in the density of holes at the surface. As you go to higher hole densities, then you end up with a reaction which turns out to go up with a third power of the density of holes at the surface. We actually hadn't expected that. I don't think anyone had expected that. At least I certainly hadn't. But this is what we observe experimentally. That it appears that there's 2 different operating regimes. One regime where we can imagine at low hole densities that the holes don't really see each other on the surface. Another regime where there seems to be some sort of cooperative effect between holes at the surface, which means that the current density goes up with a cube of the third power of how many holes you accumulate at the surface with that light. So you have Most simply the idea that the rate determining step of this third order mechanism involves three oxidized species on the surface coming together to drive the rate determining step, which is probably OO bond formation. We've taken this sort of approach of using optical signals to measure kinetics for a range of metal oxides. So this is similar data for a range of different photoanode metal oxides. And you can see in this case here, hematite is actually the slowest. Titania or tungsten oxide is much faster. And that, of course, that correlates with the idea that hematite is actually the worst material in terms of oxidizing water. It's the best light absorber of these materials, and it's the most stable, but it's certainly not the most useful. And one of the reasons it's not the most useful is because it's rather slow at oxidizing water. We can also use these sort of measurements to measure activation energies. And one of the interesting things we can see here is that the activation energy for water oxidation doesn't change as we change the hole density, at least in this third order regime, which suggests that what's happening here when we are as the reaction accelerates, it's not accelerating because we're changing an activation energy. It's accelerating just because we've got more holes. And those holes come together in a way which accelerates the reaction. Because we can measure kinetics, we can do all the sort of things which spectroscopists and kinetic people like to do. We can measure as a function of pH, as a function of temperature, and hydrogen deuterium exchange. And then we can go and talk to theorists such as Victor Batista in Yale. We can do DFT calculations to try to understand what might be happening. And Victor and his colleagues did calculations just simply on a flat hematite 110 surface. Very often people interested in catalysis imagine that catalysis happens at defect sites. Victor did his analysis assuming a flat 110 surface and was able to show that his calculations agreed rather well with our measurements. And the idea is that we can see these iron 4 oxos diffusing around on the surface. 2 come together, then 3 come together. When the 3 come together, then that enables a reactive pathway which has a rather low activation energy. It has the same pH and kinetic isotope effect behavior which we see experimentally, and that drives the OO bond formation, requiring 3 holes, which is why we see third order behavior. And then the fourth hole comes along to oxidize this species to release electrooxygen. And so this is an example of how we've used our spectroelectrochemistry combined with DFT calculations to gain some insight into into water oxidation catalysis on a hematite surface. We've used this approach to study a range of catalytic systems. And for example, we've applied it to proton reduction on a ruthenium electrocatalyst for proton reduction, to looking at organic oxidations, in this case methanol to methanol oxidation on hematite. Photooxidation, and in this case we observed second order behavior, and we could propose a mechanism based on that. And we've also used this to look at nickel iron oxyhydroxides electrocatalysts. These work well under alkali conditions. In this case, looking at how, as we change the metal doping in a nickel oxyhydroxide, the extra metal can change the kinetics, and in this case measure an experimental trumpet plot, the idea that iron works best as the dopant in a nickel oxyhydroxide because it's neither too oxidizing, so difficult to form the oxidizing species, but not so easy to oxidize that it's not reactive enough. But I'm not going to go into any of those in detail. What I thought I'd spend the rest of my talk on, for the last 15 minutes or so, is to focus on water oxidation by iridium oxide. And I know this is a particular topic of interest to BP. Iridium oxide is the state-of-the-art material used in PEM electrolyzers for driving the water oxidation. But of course, it's a highly non-ideal. It's rather a good electrolyzer, of course, and in particular, it's a catalyst which works well under acidic conditions. Most water oxidation catalysts work better under alkali conditions. But equally, of course, iridium is a rare earth metal and expensive. And we need to understand, A, why iridium works so well, and B, can we imagine strategies to either to reduce or replace the iridium loading in one of these electrocatalysts. So we started to look at some kinetics, first spectroelectrochemistry, in some of these iridium oxide electrocatalysts. And this is particularly some work initiated by Carlotta Bozan in my group. So this is a typical cycle voltammogram for an electrocatalyst, for iridium oxide, where you can see some pre-catalytic waves and then a catalytic wave here, which corresponds to water oxidation. And what we've been doing is measuring the optical absorbance of this iridium oxide as a function of potential across this cycle voltammetry wave. And what you can see here is that you see the appearance of absorbance at different wavelengths as at different stages in this potential range. We can analyze these different waves of optical signal, and you can see here a deconvolution of this overall optical absorbance into 3 distinct redox waves which have different optical fingerprints. We can then map out the potential dependence of each of those redox waves, and you can see the potential dependencies of these redox waves down the bottom here. This is the first, second, and third, and they all happen at different potentials. And of course, what these correspond to are different redox changes in the iridium oxide. And so it's the idea that different redox states of iridium have different colors, and that's why we observe different optical spectra. Now, of course, these optical spectra are rather broad and featureless and don't really give us any direct information on what the states are. And that's one of the downsides of our approaches. And so we have to rely on colleagues who do far more in-depth studies of the nature of the redox states in iridium oxide to understand what these redox waves are. But at least our measurements allow to measure the density of those states as a function of potential. And so in general, we imagine the redox 1 and 2 are the pre-catalytic waves, which correspond to the oxidation of iridium 3 to iridium 4. And then the catalytic wave, which is this redox wave 3, which corresponds to the onset of water oxidation, is associated with the oxidation of iridium 4 states, either to iridium 5 or to the oxidation of an associated oxygen. Now we can observe these redox states. We can also now think about measuring kinetics. So maybe the easiest way we could do that is we apply a potential to accumulate charges on the surface, and then we simply go to open circuit. And we look at how the signal decays. And the decay of the optical signal will tell us how quickly those states are able to oxidize water. And we can check it's water oxidation rather than anything else, because we can measure the spectrum of the states which are decaying. And when we look at the decay of the states which are associated with water oxidation, so those iridium 5 states, well, then we can measure the kinetics. What you can see here is a rather simple assay of the kinetics of water oxidation on iridium oxide. You don't have to be an expert to read off that the time scale here is seconds. Oh, I didn't have a second on the time scale. This is time in seconds. And you can see that at low potentials, it probably takes tens of seconds to react. Whilst at higher potentials, the kinetics start to happen in hundreds of milliseconds. So there's a rapid acceleration of the kinetics as a function of potential. We can compare that acceleration for water oxidation to what we observed for hydrogen peroxide oxidation. That's also an interesting process. It's kinetically and thermodynamically much easier. And so you can see here, but if you add hydrogen peroxide to your solution, then the current turns on much earlier because now we're oxidizing hydrogen peroxide, not water. Indeed, we only now see the first 2 oxidation waves with the hydrogen peroxide, because you don't need the fourth one, the third redox wave, the iridium 5 states, to drive the water oxidation. But the first 2 waves look pretty much the same with and without the hydrogen peroxide. But what gets more interesting is to measure the kinetics. So these are the data I showed a second ago, the idea that for water oxidation, the kinetics really only take off when you get to about 1.4, 1.45 volts, and then the kinetics rapidly accelerate. With hydrogen peroxide oxidation, the kinetics are almost independent of potential. There is a small acceleration, but it's not very much, just over a big potential range. In other words, hydrogen peroxide oxidation is first order. It's a reaction which is independent of a density of species. And that suggests that individual iron 4 species, iridium 4 species are driving one electron oxidations as the rate determining step, a simple reaction. Another way of putting it is that the current, if you plot current versus the density of states, or either oxidizing states, the current goes up linearly with the density of oxidizing states. But when you compare that to the water oxidation, well, then water oxidation requires, it only really takes off when you have a lot of states generated in the system, and then it accelerates very rapidly. And you can see that in how the current voltage plots work here. And so the water oxidation current turns on much more sharply than the hydrogen peroxide turns on, because the hydrogen peroxide, the current's going up just because you have more states. Here, the current turns on faster because you have more states, but also as you have more states, the kinetics accelerate. So you have the idea of cooperative effects. So the idea that when you generate multiple oxidizing species, they can interact in ways which accelerate the reaction, rather like what we observed on the hematite. And indeed, there's a nice paper by Nong et al., which came out last year, talking about cooperative effects on iridium oxide. We can do the same sort of analysis, not comparing water versus hydrogen peroxide oxidation, but comparing water oxidation on an iridium oxide film to molecular iridium dimers immobilized on a mesoporous indium tin oxide electrode. And we can see something a bit similar, that the molecular dimers, the water oxidation turns on earlier, but it doesn't turn off as sharply. Why might that be? Well, when we use our spectroscopy to measure the redox transitions, then broadly speaking, we see rather similar redox transitions at 3 waves, and would assign them to the same things on both iridium oxide films and these iridium dimers. The only real difference is we can see that the molecular dimer is shifted to slightly higher potentials to drive the oxidation of those species. What's maybe more striking is when we measure the kinetics. And this is the data I showed before on the iridium oxide film, showing these cooperative effects and the idea that kinetics accelerate very rapidly with potential. On with the molecular iridium, there's no acceleration. The kinetics are essentially independent of potential. And so this is again the same idea that water oxidation on iridium oxide films requires cooperativity between redox sites. But in these molecular dimers, then the dimers can't interact because all these big organic ligands around them stop them having any significant interaction. So the dimers have to behave as isolated systems, and therefore the water oxidation is independent of density. And this helps us understand the differences in behavior here. So the molecular system has its redox energy tuned to slightly higher potentials. And in those trumpet plots I showed you earlier of reactivity versus energetics, that would correspond to the molecular system being faster at achieving water oxidation, at least for isolated oxidizing species. And so you can see when the density of species is low, the molecular system is faster. It's a faster catalyst. And that explains why as soon as you start to generate any states, molecular water oxidation, the molecular system starts to turn on water oxidation. But the iridium oxide film wins out at high potentials because then it gets all these cooperative effects between the oxidizing species. And that means the current turns on much more sharply and quickly overtakes the molecular iridium. The last thing I want to touch on is the difference between amorphous and crystalline iridium. So crystalline iridium is the most stable, iridium oxide is the most stable form of an electrocatalyst for driving water oxidation. But it is, many studies have shown that amorphous iridium oxide is able to achieve higher current densities. And so this is a plot of the potential required to achieve 1 milliampere square centimeter. And amorphous iridium oxide is able to achieve that water oxidation at a much lower potential than crystalline iridium. But the crystalline is more stable and is currently the system used in the electrolyzers. We're interested in trying to understand this difference in current density between iridium oxide, the amorphous, and crystalline. And so we wanted to try to use our spectroscopy to measure the underlying kinetics, not just the current density, but actually what are the timescales of water oxidation for the same densities of charge, or same in these two systems. So we made two examples of iridium oxide. Essentially, first of all, made our amorphous iridium oxide, then we annealed it. We made it more crystalline. The morphology overall doesn't change very much, but the crystallinity changes dramatically. And we can see large differences in the current voltage behavior. So the amorphous iridium oxide shows much larger capacitive waves, suggesting that it's got a more open structure and that the active sites in this amorphous iridium oxide extend significantly into the material, whilst the crystalline material shows much smaller capacitive charging, suggesting it's only really the surface which reacts, and also the crystalline material has its current turning on at a higher potential. We could do all the same sort of measurements we talked about earlier, using our optical measurements to look at the redox waves in not just the amorphous, but now also the crystalline. We can again see the optical data showing that we can actually see the redox waves, which you can't really see in electrochemistry. The optical data we can see in the crystalline because we have higher sensitivity and we can discriminate the different waves much more easily. But the density of these states is about an order of magnitude less than in the amorphous, suggesting that the crystalline material has around 10 times less active sites for driving water oxidation. We can also see that the amorphous material is able to be oxidized at a lower potential, or the crystalline material. The turn on of redox wave 3, which is the catalytic wave, is at higher potentials, which from these trumpet plots I talked about a minute ago would correspond to the idea that it should be faster at oxidizing water. And indeed, that's just what we observe, that when we plot the underlying kinetics of water oxidation on the crystalline and amorphous iridium oxide, but now plotted relative to the coverage of the states, of the available states in these iridium oxides, then we find that the crystalline material, for a matched coverage of oxidized states, is about an order of magnitude faster than the amorphous. And we can imagine that because in the crystalline material, it's much easier to have these strong interactions between sites, which enables faster water oxidation. And so we end up with the conclusion that the crystalline material is not just more stable, but is actually more active than the amorphous material. The problem with the crystalline material is simply that it's got too low a surface area. And that if we could find ways to have very high surface area crystalline iridium oxide, then that may actually be a pathway to achieving higher current densities with lower total amounts of iridium. And we think that may be interesting when we think about pathways to lower the iridium content in electrolyzers. So with that, I must stop. I hope people have found this interesting. I've shown the faces and names of some of the key people who've been involved in this. This is very much teamwork and involved many collaborations, particularly as I discussed with Ivan and Reshma, but also many others from my group. Many external groups who've been essential in supplying us synthesizing the materials and helping us with the modeling and some of the other electrochemical analyses. Thank everyone who's been helping to fund this work, and of course, most recently, the bp-ICAM program. And I'll leave you with some conclusions. But in essence, I hope I've given you some thoughts that if we want to understand electrocatalysis or photocatalysis, then something as simple as measuring the UV-vis absorption spectrum operando in these electrolyzers, these electrocatalysts or photocatalyst materials, can give us quite a lot of rich information, which can help us understand reaction mechanisms and start to think about how we might be able to improve function. And with that, I think I better stop.